Bismillahirrahmanirrahim. Assalamu alaikum. This is Ayman Ibrahim, and today we're going to do an SPSS practical on linear and logistic regression. So what we're going to do in this video is 1. Apply the linear logistic regression in a real world scenario with data that has already been collected, and interpret some important results that come from the output of our analysis. So I'll give you something about regression. First, regression is basically using independent variables to predict a change in a dependent variable. So we pick a few predictive variables to create a model, and this model is used to predict the dependent variable with a reasonable degree of success. There are 2 types of regression. Primarily, one is linear regression, and we use this when the outcome is continuous or a scale. And the logistic regression, which we use when the outcome is a binary categorical outcome. There are other methods to test, a categorical outcome that is not binary. Like, for example, it has 3 or 4 categories, but that is beyond the scope of this presentation. Another description that you'll find frequently is simple or multiple regression, and this is simply how many predictors are in our model. So a simple regression is using one independent variable to predict the outcome variable, but multiple regression is using multiple independent variables to predict the dependent variable, and using multiple predictive variables is something that regression, linear and logistic, allows us to do. So first we're going to start with applying the linear regression on our data. So what we have here is a data set that has been collected, and this one, and to collect the data for this data set, we have sent a questionnaire to all the nurses in Qasim with the collaboration of the Ministry of Health in Qasim. And in this questionnaire, we have asked some demographic data, like the age, gender, education, nationality, marital status, residence, number of children. And then we also assessed some variables that we want to study as predictors for depression. So we wanted to study, test several things like exercise, smoking, type of service, if it's administrative, emergency, experience in Saudi Arabia, working hours, income, fear of litigation or being sued, the frequency of visiting their home countries, because a lot of these, or almost all of the nurses in Qasim, were expatriates. Also language difficulties, difficulty in dealing with Arabic speaking patients, having night shifts, number of meals per day, and number of breakfasts per week, if they skip breakfast sometimes, and sleep hours, average sleep hours per night, and we use that then to predict the depression score. And to calculate the depression score, we have used the DASS-21, which is an acronym for the Depression and Anxiety and Stress Scale, which is a questionnaire, a validated questionnaire, in which made of 21 questions, in which patients or participants answer questions related to depression and anxiety or stress. For this particular project, we're interested in the questions related to depression, and then we calculate the score. Like, for example, if the patient answers, I couldn't seem to experience any positive feelings at all. Does this never happen? 0. Sometimes, often, or almost always. And the more that they have this feeling, the higher score that they're going to get. So if we calculate the scores that are related to depression, like question 3, question 5, and others, then we're going to have a total score for depression. And then using this score, we're going to categorize patients into several degrees. So assuming, for example, if one participant have the score of 10, then they have moderate depression. But they have 2, they're normal, they don't have any symptoms of depression. And this is not a way to clinically diagnose them. It's a method to assess the severity of symptoms of depression. And this is something that we've been interested in studying. So, as we described in the beginning, is that we have two types of regression, right? One is linear and the other is categorical or logistic. So for linear regression, we're going to use different variables in order to predict the score itself, the number, because that is a continuous variable. And then for the logistic regression, we're going to also use multiple variables to predict the degree of depression, or the basically whether or not they do have depression. So a kind of categorical yes depression or no depression kind of outcome. All right. So let's come here and let's then dive into some regression. So to do that, we go into analysis, then we go into regression, and for that we select linear regression. So from our variables, the dependent variable is the outcome, and that would be the ASS, depression score. For the independent variables, we're going to use whatever variables that we want to use as predictors or to account for in our model, because of course you're familiar with confounders, and if you do not include factors that could be confounders in your model, you're not going to be aware, or the data can be falsely interpreted because you have not accounted for these confounders. So to select the variables that we want to include, the decision should be based on one, what has been found to be relevant in the literature. So what have been found before to be a predictor of depression, like for example, exercise have been found to be a predictor of symptoms of depression. And then factors that we want to study, like for example, we want to study whether smoking, service type, working experience, average working hours, monthly income. We want to study all of these different things as predictors of depression. And this is really, I think this here shows the power of regression in general, because it allows you to test multiple predictors at once. So let's see here, we want to add the breakfast. Let's add also average sleeping hours. We also want to account for all these differences. So we want to add age, BMI, practice exercise we've already included. One thing you have to make sure that you never do is to add two variables into the independent section that perfectly predict each other. So if we put age and age range, those two are 100% correlated. So these are going to mess up the model. So you have to make sure that all of these factors are independent, that age and gender are independent, of course. Education, nationality, they're independent, so we can include them. But if something can predict the other one completely, then they both should not be in the same model. All right, so there are many settings that we can add here, but let's for now just do it vanilla and just create this model. This is the output that we have received from our linear regression, and we have several tables we're going to look at. First of all, we have the first table here, which is going to show us our model, what are the variables we have entered, and what is our method of entering. And these are basically all the predictor variables. This here indicates the method that we have entered, and here in this case we have entered them all at once. So that is the enter method of adding variables. This is the model summary, and an important number we want to look at here is the R-square, and this basically gives us what is the proportion of variance in the outcome variable that can be predicted from our model. So that is 0.1 0.159, so about 16% of the variance in depression scores can be predicted with the elements that we have added here. So that's not bad. This ANOVA table here also gives us important information, most notably the significance. So as you see, the significance of our model here is 0.000, so that means it's less than 1 out of 1,000. That's a very good significance. And it basically tells us that our model can reliably predict the outcome. You could ask me, in comparison to what? In comparison to the average. Because the theory here, the theory behind the significance thing, is that if I ask you, can you please tell me what is the what would be the depression score in a nurse? A good way to calculate this is to just go over every nurse and then check the average. Like, for example, selecting a sample here, we have 1,000 people, 1,000 nurses. We see the depression scores, then we check the average, and then we say that the average is a very good guess. And that is fair. But what we're trying to do with a model here is to be a little more sophisticated. So what we do is we say, okay, I know that the average score, depression score for a nurse is 5, for example, out of 14, or out of 15 or whatever. That number could be true in some cases, but we can do better. We can say that, for example, from our study, we have found that a nurse who is smoking and does not exercise, is living alone, has a lower salary and longer working hours, has a depression score that is 10 or 11, compared to somebody else who does not have these factors. So what our model does here, what the significance says, is that this model, if we account for these things, we can predict the outcome more reliably than just checking the normal average. Then our third table here is the table for coefficients. And what we have here are the parameter estimates. These are the different variables that we have used. And what we really want to look at are the unstandardized coefficient, the standardized coefficient, and the significance. The significance tells us what if there is a change in one of these predictive variables, like age, gender, does the depression score significantly increase or significantly change? So what we see here, for example, is for practice exercise, there is no significant change. So despite what we have previously thought or have previously considered, in our sample here, the fact that the participant reports exercising does not significantly predict their depression score. But if we, for example, look at a different variable here, like nationality, nationality is a significant predictor of depression. So that perhaps that could have a cultural component. If we look here, fear of litigation is an important factor, right? This one is significant. Difficulty in dealing with Arabic-speaking patients. This is a big problem. Apparently, it affects symptoms of depression among these people. Meals, having meals, less meals per day is predictive. Having less breakfast is predictive, right? And average sleep hours is also predictive. So, as you see here, we have found a few elements that are significantly influencing the outcome. And this doesn't mean that the other factors have no effect. That means that change in them, when we have put this model in this way, change in the other variables does not significantly change the outcome variable. Another important column we need to look at is the B. And this B simply is giving us an idea about the unit change. I mean, if there is a change in one unit in the predictor, what is the change that we expect in the outcome? So check here, for example, the average sleep hours per day. The unit here was hours, so 1 hour, 2 hour, 3 hours. And this here tells us what is the effect of an increase in hours on the depression score. So minus 0.326, that means for every increase, for every 1 hour increase in sleep, we have a minus 326 decrease in the depression score. So that means the more you sleep, the less depression score you have in our sample. Right? Breakfast per week and meals in 2 groups, those are categorical predictors. So this will be affected by how we have defined our labels, basically. So here, meals in 2 groups, if we would like to check back our variable here, in meals in 2 groups, 0 indicated 2 meals or less, and 1 indicated 3 meals or more. So when we move from 0 to 1, what is the effect that we see on the depression score? As you see here, there's a decrease of almost 1, right? 0.9. So that means if you have more than 2 meals, right? As we have said here, if you have 3 meals or more, then you're going to have a score that is less by 0.9 in depression. So that means also more meals per day is inversely proportional with depression score. Same thing can be said about the breakfast, nationality, etc. Let's do something a bit different. Before we do that, perhaps also a standardized coefficient here is something we also need to know is basically the same thing as the B, but after standardization of units. Because as you see here this one is measured in hours, this one is measured, in how many times per week. Those are different units, and that does not allow us to compare different the effect of different variables to each other. But once we have a standardized coefficient, then we assume that all of these have been measured in the same unit. And once they have been measured in the same unit, we can now compare them. So we can look here and say that, a change in the frequency of breakfasts per week has a bigger effect than the meals per day, right? Or than sleep hours. We look here that working experience in Saudi Arabia has very limited influence compared to the others. Alright, so now that we've done that, now let's try to mess with the settings a little bit. So let's go back again to Analyze, to Regression, and then Linear. And again, we select these variables, the dependent variable, the depression score, and let's use all the others as independent variables, or maybe not all of them, except for the, we don't need to have 2 for age. We don't want depression, that's the outcome. We're going to have 2 for sleep hours, all right? And what we're going to change now is the method of entering the variables. So the method that we've tried at first is enter. That basically just creates a model with all the variables at once. But if we change these, and as you can see here, there are several different ways to do this. If we change it to a stepwise approach, the stepwise method basically starts with an empty model, and then one by one adds the most significant predictors. So adds the most significant predictor and then tests the model, then adds the second most significant predictor and tests the models, and excludes any predictors that are not significant. So this is a good way to kind of help you understand how your data, or what variables in your data are predictive of the outcome compared to others which have less predictive value. And let's also mess around with the settings here. So in statistics, we can add the confidence intervals for our estimates. It's going to be valuable. We can also add the R-square change. And as we've said, the R-square basically lets us know what's the proportion of the variance in the outcome is explained by the model. So we're going to see, as we add more variables, how the R-squared is going to change. In plots, let's have also the standardized residual plots, histogram, normal probability plot. The residuals are basically the differences between the average and the basically the difference between the predicted and the real result. So in different data points, we have a model that predicts the data points, and then there are the true data points of the data. So the sum of the differences between the real data and our predicted data basically tells us how accurate or how capable our model is of predicting those data points. And this is what we call the residuals. So we're going to have a look at these in these figures. In save, we're not interested in this right now. In options, this here you set basically the criteria for which variables are entered and which variables are removed. So you're going to keep this as the default. The style, we change the style of the table. The style of the table for now is fine. So if we press OK and see what we have. So you see here we have now multiple variables, and then with each iteration we're adding a different variable included. So we have different models and we add a variable each time. If you look here, this is the model summary. Look at the R-square change. It's increasing a little bit every time. This is our ANOVA, the significance, you see. So the significance, they're all significant. All right, so that's good to know. And then if you can go down here, these are the coefficients or the parameter estimates. And as you see here, for the first model, there was only one variable, and that is fear of litigation, because that was the most significant predictor in our sample. And then it has, standardized beta. But then when we include another variable, like, having breakfast per week, it changes a little bit, because now we're accounting for other variables to be in the model. So when we account for other things, it explains away part of the prediction of the fear of litigation, or fear in nationality, breakfast per week, etc. As you can see here, all of these are significant, because that's basically the rule that we have decided on when we have created the stepwise model. And if you can see here in model 6, we don't have as many predictors as we had in the past, but all of these are significant ones. And if you can go back here, if you can check the R-square for the 6th model, you see it has a 14% or 14.4% explanation of the outcome. So that is not as different as from the model that we had, because the one we had at first with every variable was about 16%. So this is doing the very similar amount of prediction with much fewer variables. So now we're basically being very parsimonious. We're being more we can do more with less variables, you see. And those are the excluded variables, because the significance was not what we was not enough, or was not important for us. So yeah, so that was linear regression, and now then we're going to move on to the logistic regression. All right, so now we're going to do the binary logistic regression, which is, again, as we explained, is the type of regression we use when our outcome variable is binary, one of two options. So for that, we're going to go to Analyze, Regression, Binary Logistic. And in the dependent section, we're going to choose depression in two categories, which is our binary variable for depression. In this one, 0 means normal, 1 means depression. And for the covariates, we're going to keep this simple. I mean, binary logistic is complicated as it is. So let's pick, meals, breakfast per week, and age. So now we have like two categorical predictors and one continuous predictor, right? So we're gonna go, when we have categorical predictors, we have to define them in this categorical window. So now we have meals in two groups and having breakfast per week. For both of these are categorical covariates, and then we decide which one of the options inside the category is going to be the reference category. So in the case of meals, 0 is 2 or less meals, and then 1 is 3 or more meals. So we're going to keep the reference category the last, so that means we're going to compare people who eat less to people who eat more, right? In breakfast, we have 3 categories, and also we're going to use the last one. So people who eat like eat breakfast 3 times a week are compared to people who eat 6 or 7 times a week, and then people who eat 4 or 5 times a week are also compared to the same last category, people who eat 6 and 7 times a week. All right, so people who eat a few times to people who eat almost always, and then people who eat sometimes to people who eat almost always their breakfast. All right, we're also going to go to the options, and here it's useful to have the confidence interval for our odds ratio, because that's the result we're going to get. And also Hosmer and Lim show goodness of fit, and this is gonna help us see how well our model fits the data. All right, so I think this looks good. Let's go. So this is the outcome we're getting. As you see here, this is the coding for the dependent outcome variable. And this is the coding for the predictor variables. As you see here, meals in 2 groups, 2 meals or less is 1, and 3 meals or more is 0. But in breakfast per week, because we're gonna get an odds ratio, you have to compare one group to another, right? So when we have more than 1 categories, we have to, for the first coding, we compare up to 3 meals with 6 to 7 meals. And then in the second coding, 4 to 5 times, then compared to 6 to 7 times, right? So that's why we have 2 in this case. The 0th block is showing us an empty model, and what we call the null model. And this basically, what this model is that it predicts everyone to be depressed. So, and it tells us now, what if we predict that everyone in the sample is depressed? What is the accuracy, basically, overall accuracy of this model? And why does SPSS calculate this? Because it's going to compare our model to this model. So it says, what if we don't have any predictors? What is the result? And then what if we have these 3 predictors we've picked? What will be the result? And then we compare, are they significantly different? And if they are significantly different, then we know that our model at least contributes something, right? So we're going to move on to the model we've created here. And we can see here in the chi-square, it is our model is significant. So that's good. That means our model has a significance, or the prediction of our model is significantly different from whatever an empty model does. If you can also go here, this one, the Hosmer and Lim show test, this is the test of goodness of fit. And we can see here that it is not significant. And this is actually good in this case, because non-significance in this test indicates goodness of fit. Here we can see a classification table. which basically classifies our sample to depressed and non-depressed as observed in the data, and then depressed, non-depressed as predicted by the model, right? So what we have here is 51% of normal people were correctly identified as normal, and 71% of depressed people were correctly identified as depressed. So this simply is the specificity, and this 71% is the sensitivity of our model. And then this is basically the meat of our model. This table tells us the predictive value in odds ratios of each element of our predictors. So if we look here to the first one, meals in two groups, it is positive. The B here is positive, and that means there is a positive prediction when we compare people who eat less to people who eat more, because that's how it was defined in the first table here. We're comparing people who eat less to people who eat more, and that's positive. So that means people who eat less are more likely to have symptoms of depression. And when we look here, that relationship is significant. And XB, or exponential of B, is basically, in simple terms, the odds ratio. So the odds ratio in this case is 1.8. And we can interpret this as people who eat 2 or less meals per day are 1.8 times more likely to be depressed or to have symptoms of depression than people who eat 3 or more meals a day. If we also look here, this is the variable we have with more than one category or more than 2 categories. This is not binary. So here we have, if we compare the first one, and which was the first one here, the first one was up to 3 times breakfast, up to 3 times per week. Having breakfast up to 3 times per week compared to having breakfast 6 to 7 times per week, or almost always, is positive. That means it predicts more symptoms of depression. Here also, having breakfast sometimes per week is also predictive of having symptoms of depression compared to people who eat almost who never miss breakfast. And also here we can look at the odds ratio. Both this relationship here is significant. We can look at the odds ratio. So they are 1.6 times more likely to have symptoms of depression. Interestingly, the second dummy variable here is not significant. So that gives us the information that people who eat breakfast sometimes do not have a significantly higher symptoms of depression than people who eat breakfast every day. But the cutoff here is people who rarely eat breakfast per week or have it 3 times or less. All right. If you also look at the age here, the age was a continuous variable. The one we picked was continuous. And that means that the numbers we get here is per unit change. So first of all, it is significant. And second of all, for each 1 year increase in age, we have 0.97 likelihood, we multiply the likelihood by 0.97. So that means we have less likelihood of depression with increased age, right? And if we want to make that a bit easier to interpret, maybe we can pick up a calculator and check out divide 1 by 0.97, and this basically gives us the reverse. It tells us that the less, when you have a decrease in age, if you have a participant that is 1 year younger, they are 1.03 times more likely to be depressed. So although it is significant, it is a bit of a weak relationship, as we see in this case. And hopefully by now you are a bit more comfortable with regression, and hopefully you can make your own results. And good luck.